Hi everybody. This is the second video about modeling, and in this video we are going to look into black box modeling in the frequency domain. Suppose we have this system, this unknown system or unknown process, which could be an electromechanical system driven by a motor. And we want to analyze this system in frequency domain, so we want to have a Bode plot, because when we have the Bode plot of the system, we can analyze what kind of system it is, and we can derive the unknown parameters out of that Bode plot. So what are we going to do? Well, first of all, we bring this system in a so-called operating point. So what we do is we apply an input set point to the motor, probably a voltage. So we set a voltage to the motor and the motor starts running. And for instance, we measure the position of the motor by measuring an encoder. So we measure the YT over here. So then the motor is running and we log the data over here. Then we add so-called noise to the input signal, white noise. And white noise has all frequencies up to the Nyquist frequency, which is half the sample frequency in the signal. And the system starts to respond on that noise. And then we have this, for instance, as a noise and this as a system behavior. And we log the output and the input, and then we can make use of the MATLAB system identification toolbox in order to derive a Bode plot out of it. And one of the functions we have to use is the TF estimate function, which is available in MATLAB in that system identification toolbox. Well, this video is not about system identification, but about how can we derive a system description, a transfer function out of a Bode plot, and how can we derive the relevant parameters. So when, for instance, we have this kind of a transfer function, well, how can we derive the transfer function out of it and the relevant parameters? So we have to know the basic systems because they are important for the complete process. Well, we are going to do an exercise. Suppose we have a measurement and we see this as a Bode plot. This is the Bode amplitude plot, the blue curve, and this is the Bode phase plot. In this Bode plot also asymptotes have been drawn. An asymptote over here and one over here. And then we see two things. Well, first of all, when we look to the low frequency and high frequency behavior of that system, we see that the low frequency behavior is constant, and at high frequencies we see that the amplitude plot drops by minus 60 dB per decade. So first of all, it indicates that it's a low pass filter, and the minus 60 dB per decade indicates that this is a third order system. Remember, a first order system has a slope of minus 20 dB per decade at high frequencies, and a second order system has a slope of minus 40 dB per decade. So minus 60 dB per decade should indicate that we have a third order system. So this could be my transfer function for my system, which I analyze from the Bode amplitude plot. H is a constant value k divided by 1 plus j times omega times tau 1 time constant number 1 times 1 plus j times omega times tau 2 second time constant times 1 plus j times omega times the third time constant tau 3. Well, what we also see is when we have drawn these asymptotes that we have a cutoff frequency here and we have a cutoff frequency here. And especially this is interesting because here my Bode plot drops from minus 20 dB to minus 60 dB. So when we have a cutoff frequency over here, then most of the times this amplitude drops from minus 20 to minus 40 dB. So when it drops from minus 20 to minus 60 dB per decade, it should indicate that there are two time constants involved at this cutoff frequency. So two time constants should have the same value. So in that case, that tau 1 and tau 3 should be the same. So in that case, my transfer function can be written as k over 1 plus j times omega times tau 1 times 1 plus j times omega times tau 2 and that part squared. And from these cutoff frequencies, we can calculate the time constant. Remember, the time constant is 1 over the cutoff frequency. So, well, let's have a look over here. This is 10 radians per second, this is 20, this is 30, and this is 40 radians per second. So time constant number 1 is 1 over 40, which is 0.025 seconds or 25 milliseconds. Here we see the drop from minus 20 dB per decade to minus 60 dB per decade. And as we discussed, tau 2 and tau 3 are the same time constants and they are equal to 1 over this cutoff frequency, which is 1 over 100 radians per second. So tau 2 is 1 over 100, which is equal to 10 milliseconds or 0.01 seconds. So now we have the time constants and we know exactly what the transfer function will be. Tau 1, tau 2 have been identified, so the only parameter left is the k. This is a low pass filter, so for very low frequencies, this is a constant value. So the frequencies up to 0 radians per second, this is still a constant value. And what we see over here is that when omega is 0, then the complete part and the denominator is equal to 1 because we can neglect these imaginary parts for this omega is 0 value. So for a value of omega is 0 or almost 0, the transfer function h is equal to k over 1 is k. So by looking to the both amplitude of at very low frequencies, as omega is near going to 0, very near to 0, we can calculate that k value. So let's do that. We look to the DC gain over here and we see that it's almost 10 dB. So when this is 10 dB, it should indicate that 20 times the log of the transfer function, which is k for very low frequencies. So 20 times the log of k is that 10 dB. So now we can calculate k out of this expression. Well, log of k is 10 over 20, which is 0.5, so k is 10 to the power 0.5, which is equal to the square root of 10, which is 3.2. So this is my transfer function. H is equal to 3.2 divided by 1 over j times omega times 0 times 0.025 times 1 plus j omega times 0.01, and that expression squared. So that's all. Or not. No, that's not all. Because we haven't looked to the phase characteristic. And what we know from a third order system, that when we have a third order system, our phase should end up at 270 degrees. And why is that? Well, remember when we had a first order system, the phase ends at higher frequencies at minus 90 degrees. For a second order system, it's minus 180 degrees. So for a third order system, which is this system, which we have indicated and defined from that Bode amplitude plot, for the third order system, we expect a phase, a lag of minus 270 degrees for higher frequencies. But this phase characteristic keeps on dropping and dropping. So there is only one basic system which can give this system behavior, and that is a delay. So there is a delay in this system, and this delay should be added to the transfer function over here. And in that way, we get another or a new transfer function, which is equal to the original one, multiplied with the transfer function of a delay. And the transfer function of a delay is e to the power minus j times omega times the delay time tau d. So this has to be added to our transfer function, and we have a new parameter in our transfer function which we should identify. Well, how can we do it? What we are going to do is we are going to look to a specific frequency at which the delay behavior is very good visible. And we are going to look to a frequency and to a point in our figure, in our phase plot, which we can easily read out. And a good one is this frequency over here. At 40 radians per second, we can see that the phase is minus 180 degrees. Remember, we have to calculate the phase in radians because there are also omegas in radians per second in my phase description. So we have to say, well, at a frequency of 40 radians per second, my phase is minus p radians. All right, so when we know that, this is the phase at a certain point. We could also pick another one, for instance, at this point, but we have chosen that one. Now we can write down the complete expression for the phase using this transfer function, and we can fill in the frequency which we have chosen over here, and we can fill in the frequency, the phase which we have measured over here, and then we can calculate the time constant tau d. So the phase of a system is the phase of the numerator minus the phase of the denominator. Well, let's do the calculation. The phase of the numerator is the phase of this part plus the phase of that part. This is a real number, and this is in a complex plane on the real axis, so this is a phase contribution of 0. Well, the phase of a delay, the phase of an exponential complex number, is in the power of and the exponent of this expression. So it's everything in this expression. So yeah, everything in this exponent, I should say, everything except for the j. So it's minus omega times tau d. So again, the phase from a delay is in the exponent of my complex number. So it's everything except for the j, so it's minus omega times tau d. That's written over here. So that's the phase of the numerator. Now we have to subtract the phase of the denominator. Well, that's the phase of this part and the phase of that part, and the whole should be subtracted from the phase of the numerator. Well, the phase of this part can be calculated as the arctangent of the imaginary part, omega times 0.025 divided by the real part 1. So it's minus the arctangent of 0.025 times omega. The phase of this part should also be subtracted, which is the arctangent of the imaginary part, omega times 0.01 divided by 1, which is minus the arctangent of 0.01 times omega. But there's a square over here, so we have to subtract it twice. So there's a 2 in this expression. And that complete expression should be equal to the phase at a certain point. And we have chosen for the omega 40 radians per second, so we fill that in for every omega over here in this expression, and then that phase should be equal to that 1 minus 180 degrees calculated back to radians, so minus p radians. So then we get minus 40 times tau d minus the arctangent of 0.025 times 40, which is 1, minus 2 times the arctangent of 0.01 times 40, which is 0.4, has to be equal to the phase of minus p radians. Well, we can calculate it. Minus 40 times tau d minus the arctangent of 1, which is p over 4, minus 2 times the arctangent of 0.4, which is 0.76, equals the minus p. And when you calculate the tau d out of this expression, we see that the tau d is equal to 40 milliseconds. So now we have defined the last parameter of this transfer function, and the complete transfer function is now equal to this expression, 3.2 times e to the power minus j times omega times 0.04 divided by 1 plus j times omega times 0.025 times 1 plus j times omega times 0.1, and that expression squared. So, conclusion, you have to take into account both the amplitude plot and the phase plot, and again, you have to know the basic systems to be able to derive the transfer function, the correct transfer function, and the correct parameters. So thank you for watching, and I see you in the next video.